Okay, so the first part of the project is due next Wednesday. So it consists of to talk about your data, to talk about the exploratory data analysis. So I know some of you might still haven't found a teammate because we are doing like this virtual meetings. So if you have not found a teammate for your project, so please send me a private message here. So I can help you to form groups. Okay. Okay. And also, so any questions about the midterm? Yeah, so the midterm will cover everything after the first midterm and before last Wednesday's class. Okay. Okay. Yeah. So. Yeah, so if you have questions about the midterm, so please let me know, okay? Okay, so today we will start a new topic. So we will start a new topic, the non-stationary model topic, and it is sometimes called the ARIMA model. So, so the ARIMA model consists of two parts. I think it is. Does it have here? Okay, no. So the ARIMA model consists of two parts. So the first part is the ARMA model. The second part is the integrated model. Right? So we have seen the ARMA model a lot. And the integrated part, actually, we also have seen that. So the integrated model is basically the difference model. Okay, so it's that we will first do the first differencing or the second differencing of the data to make it stationary. Okay, so the integrated model is basically the difference model. The ARMA model is the ARMA model. So I think you have like seen both of this a lot, and we have like went through the theories of both of like this model. So I think you know both of these models very well. So I think for this chapter or for this part of the course, I just help you to review those knowledge and give you some more examples and also maybe to put some things in a more formal way. Okay, so so let's start with this chapter again by an example. So this example is temperature readings from a pilot plant observed every minute. Okay, so it's a temperature reading. So you can see, what you can see from this graph is that it does not have consistent mean. It does not have a constant mean, right? It's the temperature looks to me, it is decreasing. And also, we do not find like constant variance of this from this data. So the variance is heteroscedasticity. Okay. So from that observation, we know that this temperature reading is not a stationary model. And in other words, we cannot use the ARMA model to fit it because it is not causal, it is not invertible. So the everything based, I mean, everything built for the ARMA model actually does not work for this data. If you just like pull this data to an ARMA model, it won't work because the underlying assumptions do not hold. Okay, so in order to use the ARMA model to fit this data, yeah, and also like this, slide number 3 give you the ACF plot of this data. So you can see that the ACF dies down very slowly. So this is opposite to our like knowledge of a stationary model. So for a stationary model, the ACF usually dies very quickly. So it usually like goes this like number of the ACF usually goes within this confidence intervals very quickly. But if we just use this raw data, you will see that the ACF dies down very slowly. Okay, so in order to use the ARMA model to study this data, we want to make it a stationary data. Okay, right. So yeah. So as I discussed earlier, there are many types of non-stationary behavior just by looking at the raw data. For example, it has changes in the mean, it has changes in the variation. Yeah, and I think for the purpose of this chapter, we will mainly focus on the changes in the mean. Okay, so for now, we will just ignore the heteroscedasticity of the variance of the data. Okay, so for now, we will just focus on the change of the mean. Okay, and we know that in order to make the mean constant, our tool is to make some difference. Okay, so we can make the first difference. So the first difference is that to use the current period value minus the second period value, or the early period value, okay, to make this data stationary. So this is sometimes called the first order difference. And if the first order difference does not work very well, we can also do the second order difference. Okay, so which is the first difference of the first difference. Okay, and we usually do this if this data has a quadratic pattern. Okay, and we will do the first difference usually is the data has a linear increasing pattern or linear decreasing pattern. Then we will use the first difference. And if the data has a quadratic pattern, a quadratic trend, then we will use the second difference. And also we can also do the third difference, even though in practice it is rare to go beyond the second differences to achieve stationary. But of course, if you find or if you detect that your data has a cubic trend, then you can use the third difference, okay, which is totally fine. Okay, so this is a graph that we difference our temperature readings. So this panel number A is the graph of the raw data. So we see that there's a decreasing trend. And this panel or this graph number B is the first differencing data. Okay, and this graph number C is the second differencing, and this graph number D is the third differencing. So we see that starting from the first differencing, we see that the mean becomes constant. Okay. Yeah, so you can see that the first differencing, second differencing, and third differencing are very similar. Okay. Yeah, and as I said, for now, we still see some like heteroscedasticity of the data by the first differencing, second differencing, and the third differencing. But as I said, for now, let's just ignore the heteroscedasticity. Let's just focus on the mean of this data. Yeah, and as you can see, that's the mean of first differencing, second differencing, third differencing are pretty constant. So that means that we may achieve the stationary in the sense of the constant mean. Okay, and we can also check the ACF to see whether we achieve a stationary data. So again, this plot is the ACF of the raw temperature data, and as we can see that this ACF dies very slowly. However, if we do the first difference and the second difference, the ACF dies at least like faster than the raw data. Okay, so yeah, and more importantly, we do not find significant difference of the ACF plot between the first difference and the second difference. Okay, right. So yeah, so this is what I just discussed. So it looks like there's not much difference in the behavior between the first difference and the second difference, and also even the third difference. Okay, and yeah, and we can see that the ACF plot shows some stationary when we go to the first difference. Okay, yeah. So to study this data, all we need to do is to take the first difference, and then we will just apply this first differencing data to our AMA model. So we'll just fit an AMA model to the first differencing. Okay, that's basically what we do here. And from here, we will just do everything exactly the same as our AMA model. Okay, so the logic here is like this. So we will look at our raw data. And if we find some non-stationary pattern, if we find a linear pattern, we will do the first difference. If we find a quadratic pattern, we will do the second difference. And if we find a cubic pattern, then we will do the third difference. And after we do the difference, we will check whether we actually achieve a stationary data. And to do this, we can plot the difference data, and we can plot the ACF to check if we achieve the the stationary pattern. And after that, if you believe that now your data or your difference data achieves the stationary pattern, all you need to do is to fit an ARMA model and do all the steps that we discussed early in the class, right? We will fit ARMA model, we will do the model diagnostics, we will do the model selection, and if necessary, we will also want to do a model forecasting. Okay, so all the steps exactly the same as the ARMA model. Okay, so any questions? So that's basically the ARIMA model. Okay, because we have seen the difference early, we have seen the ARMA model early. So I mean, this part is just, just like given for free. Okay, so any questions here? Okay, yeah, I think you should be good at, very familiar with all this stuff and should be good. Okay, yeah, and also, for those of you who come in late, I just said that if you still haven't found a teammate for your project, just send me a private message here so that I can help you to form groups. Okay, so now let me talk a little bit theories of the ARIMA model. Yeah, I mean, like for most part, you have seen that, but I mean, there are still some like difference between the ARIMA model and the ARMA model I want to point out about the theories. So let me switch to the whiteboard and talk about those theories. Okay. So today's class, we're doing ARIMA. And the readings is BK 4.1 to 4.2 SS 5.1, and we will also do an R code today. Okay, so let's talk some theories of the ARIMA model. Yeah, so as I said, the most difference, the most significant difference between the ARIMA model and the ARMA model is that we have this I. Okay, this I is for integrated. And an easy way to understand this is just to think it as a difference model. Okay, so that's just the key difference between the ARIMA model and the ARMA model. And the reason that we want to do this difference is because we want to make the model stationary. Okay, so let's just see some examples of the differencing. So for most of the examples we have either seen in early class, or I have already asked you to do homework, or also seen it in the exam. Okay, so this is the standard random walk model. Yeah, so it looks like an AR1 model, but unfortunately, this is not a stationary model. It is not causal, it is not invertible. It is not causal. The reason is that the coefficient of this AR1 model is equal to 1, which is larger or equal to 1. So that means this is not a stationary model. Okay, and in order to make it stationary, we can just take the first difference of it. Okay, so delta xt minus xt minus 1 equal to wt, and this wt is the white noise. Okay, so we achieve a stationary model. So the first difference of the random walk is white noise, and that means it is stationary. Okay, so we just use the first difference to transform a to transform a non-stationary model to a stationary model. Okay. And the second example is trend regression. We also seen this example in early class. So xt is beta 0 plus beta 1 t plus wt. Okay, so wt is again the white noise. So we know that this is trend regression is not stationary because if you take the expectation on both sides, it's going to be equal to beta 1t. So not independent of t. So not stationary. And to make it stationary, easily saying that because there's a linear trend here, okay, so the idea to address a linear trend is that we will take the first difference, okay. Okay. So the delta xt is equal to xt minus 1, which is equal to beta 0 plus beta 1t plus wt minus beta 1 plus beta 1t minus 1 plus wt minus 1. Okay, it's gonna be equal to beta 1 plus wt minus wt minus 1. Okay, so both of these are white noise. This is constant. Just recall our, I think, second question of midterm 1. So the linear combination of the stationary process is also stationary. Okay, so that means this whole thing is stationary. Or in other words, the first difference of this trend regression is stationary. Okay. And also, we have a quadratic trend in our model. So xt equal to beta 0 plus beta 1. Okay, let's include beta 2 t squared here, wt. Okay, so this is a quadratic trend. And this is a linear trend. Okay. So again, if you take the expectations on both sides of this model, you will find this is equal to beta 1t plus beta 2t squared. Not stationary. Okay. Yeah. And in order to make it stationary, use second difference. Okay. Right, so I think here I will just show you how the second difference work. So the first difference, delta xt, is equal to xt minus 1. So this minus wt minus 1. Okay, so this would be equal to beta 1 plus beta 2. Here should be square 2t minus 1, right? This beta 1 plus 2 beta 2t minus beta 2. And if you take the expectations on this first difference in data, it still depends on t. Which means it is not stationary. But you will notice here that the first difference here, after we take the first difference, this model only has t. Okay, so we get rid of the t, we reduce the t squared to t. Okay, even though it is not stationary, but it is better than the quadratic trend. So we reduce the quadratic trend to the linear trend after we take the first difference. Okay. Right, and if we take the second difference, so it's delta xt minus delta xt minus 1. Okay, so this would be equal to beta 1 plus beta 2, beta 2, beta 2 plus 2, beta 2t, wt minus wt minus 1 minus wt minus 2. Okay, and if you solve this, this is 2 beta 2 plus wt minus 2 wt minus 1 plus wt minus 2. So again, all these things are white noise, and this is constant. And we know that a linear combination of the stationary process is stationary. Okay. So that means if we take the second difference of this quadratic regression, we will get a stationary model. Okay. Okay, so I think, yeah, all these examples, you should be very familiar with all these examples. So now let's introduce some notations, okay, just to write things easier. So we will use the backshifter. So this will make our notation much easier. Okay, so just recall the backshifter. So bxt is just equal to xt minus 1. All right, so based on this, xt minus 1 is xt minus bxt, so it's 1 minus bxt. Okay, so this is the first difference. Okay. It's the second difference is, yeah, so let's use this notation. So let's call this delta t. Okay, then the second difference is, sorry, delta x t. Then the second difference, we will use this notation, delta square xt is equal to 1 minus b square xt. This is actually xt minus 1 minus xt minus 1 minus xt minus 2, right? And this part is 1 minus b, 2b plus b squared xt. And if you expand this, this is xt minus 2b xt plus b squared xt. So this is going to be equal to xt minus 2 xt minus 1 plus xt minus 2. Xt minus 1 minus xt minus 1 minus xt minus 2. Okay, so you see the left-hand side is equal to the right-hand side. Okay. Yeah, and for these differencing, we denote delta to the power d xt is equal to 1 minus b to the power dxt. So that's the d's difference. Right, you see that if we choose d equal to 1, then let's go back to this. If d is equal to 2, we go back to this. Okay, so by using this notation, let me introduce the formal definition of the ARIMA model. Okay, so a process xt is said to be ARIMA BDQ if delta d xt, so which is equal to 1 minus bxt, is ARMA. Okay. Right, so the here is that several things you need to check here. So so after taking the d's difference, your data will satisfy ARMA PQ requirement. Okay. The ARMA PQ requirement consists of like the causal, the invertible, and also it needs to have like those ARMA setup. Okay. Yeah, and in general, we write our ARIMA model as this. So so this phi b is the AR part, right? And this 1 minus b to the power dxt is your integrated part, okay, so which is your differencing part, okay? And this theta b is your MA part. Yeah, and here we can actually show that this alpha, which is a constant, is equal to this. So yeah, the constant is not that important. And as I discussed earlier, if you already take them, if you're already deeming the data, then this constant is equal to 0. Okay, so it's not important, but if you do not deeming the data, then you will have a constant term in this regression, and this constant term can actually be solved by the AR part and also the mean of your difference data. Okay. And also just to recall, for a ARMA PQ model, we write our model as phi b xt equal to alpha theta wt. Again, this is our AR part. This is our MA part. The difference is that in this part, we do not have an integrated part. We just use the raw data. But in the ARIMA model, we will use this difference data. Okay, so that's a key difference. And every other thing is exactly the same. Okay, so you can basically treat this first differencing data like as your xt in the ARMA model, which is also another way to look at this model. Okay. Let me see, there's a question. So I'm assuming SRAMA model is written in the symbol, correct? Yes, exactly. So the SRAMA model, the components to the SRAMA model is that S, right? And that S stands for seasonality, okay? And you are right. So we actually have another way. I mean, we have one way to express that seasonality also like in this, by using these backshifters. Yeah, you are absolutely correct. Yes. Right, so you can see that everything is built upon the ARMA model. Yeah, so yeah, the ARMA model is very important, and I think luckily we have seen the theories a lot of the ARMA model. We know how to check the ARMA model, what is a valid ARMA model, and we know how to do the model selection. We know how to do the model diagnostics of the ARMA model. Yeah, so I mean, the other features like this integrated feature and also the seasonality feature are all built on this ARMA model. I mean, built on some transformations of the ARMA model. Okay. Yeah, so if you know the ARMA model very well, like this integrated part, the seasonality part is just, I mean, a piece of cake for you, not a big deal. Okay, so very good. Okay, so that's the one difference, I mean, actually the key difference between the ARIMA model and the ARMA model is this integrated part or the difference part, okay? And another subtle difference is the forecasting. Right. So the forecasting of the ARIMA model and the ARMA model is a little bit different. Okay. So let me talk about this difference in a little bit more detail. Okay. So in ARMA forecasting, we forecast or we predict x, say x, let's say x plus m given n, right? So for example, we predict xn plus 1 by x1 all the way to xn. However, here in the ARIMA forecasting, we forecast what? So we actually forecast x. Let's just use this example to make things easier. So we forecast xn plus 1n minus xnn, right? So the idea is that we do not predict xn minus 1n. Instead, we predict xn plus 1n minus xnn, right? So we forecast this difference because the regression we run is all based on this difference. Okay, so we do not run the regression of the raw data, but we run the regression of the difference data. But however, our main interest or our main interest or our main goal is to forecast the raw data, right? We might have some interest of the difference data, But the reason that you do this difference data is because the raw data is not stationary. So we transform that to our difference data and the round regression. So I mean, the ultimate goal for you should be the raw data. Okay, so you want to predict this part. Okay, so that's your goal. But instead, you predict this. Okay. Yeah. So the question is that, can we get xn plus 1n from our forecasting? Okay. So can we get our mean interest from our forecast? Okay. The answer is yes. And it is actually very easy to see why it is yes. Okay, so xn plus 1n is equal to xn plus 1n minus xnn plus xnn, right? Because we observe the n data, so xnn is basically xn. So this is our forecast from our first differencing model, I mean any differencing model, and this xn is from the data. So you can see, which is very nice, right? So we can construct our mean interest xn plus 1n by using the forecast and our data. Okay. Yeah, and here we are just doing like the one step ahead prediction, and this can be generalized. Yeah, we're doing here one step ahead forecasting and the first differencing forecast, the first differencing data. So this can actually be generalized to any step ahead forecasting and any ARIMA model. Right. So the idea is just this. So you will use the data and the forecast, and after some algebra, you will find your main interest. Yeah, but you need to do this with. I mean, if you want to do it by hand, you definitely need to do it like very carefully. The algebra here is actually not that straightforward. Okay. Yeah, but luckily the R code can help us to do all those stuff. Yeah, so if you want to just use the computer to help you to do this, it's just very easy. And the code is just the the S-ARIMA 4, okay, which is a code that we used in last class. I mean, in previous classes. Okay, so to construct the forecast of like the future value by using this ARIMA model, perhaps it might take some work, but it is definitely doable. The hard part is actually the mean squared prediction error. Okay, so the hard part is the mean squared prediction error, MSPE. Okay, so xn plus n over xn plus n squared. So the mean squared prediction error. Okay. And this is sometimes denoted as Pn plus m given that. Okay, so we want to study the expected value of our predicted m ahead forecast and our true m ahead like observation. Okay, yeah, actually to show this is actually not easy, yeah, but you can show that this is approximately equal to, so this is just approximately equal to sigma w squared. So the sigma w is the variance of the white noise. Okay, so it is a weighted value of this. So it's times j plus n minus 1 psi j squared. Okay, and this psi j is your causal representation forecast. Okay. Yeah, and let's also recall the mean square prediction error of an ARMA model. Yeah, this is just equal to this. This is again the causal representation coefficients. So you can see that the mean square prediction error of the ARIMA model and the mean square prediction error of the ARMA model are pretty much same. Yeah, at least like from notation, they are the same. Okay, but they actually have a very, very, I'm sorry, excuse me. So they actually have a very huge difference here. Okay. If you just look at this expressions, they are actually very similar, but they are actually very different. Okay, so for the ARMA model, we know the model is causal and we know the model is convertible. Okay, so in the ARMA, the model is stationary. So that means the psi j, which is their causal representation. If you just recall from your homework or the examples I give in class, this psi j will converge, will decrease to 0 or converge to 0 as j goes to infinity. Right? So that implies this MSPE will converge. However, for the ARIMA model, the model is not stationary. So that means the psi j does not converge to 0 as j goes to infinity, which further implies their MSPE will diverge. It might converge, but in most cases, it will diverge. Okay. We will see an example later. Okay. Right, so that's a key difference, and that's, it looks like a very subtle point, but it's, just by looking at the expressions, they are the same, but what the meaning of those expressions are actually very different. And the reason is coming from the stationary. Okay. Okay. So yeah. Okay. Yeah, so that's basically, I think, the two main difference between the ARMA model and the ARIMA model. One is their difference. One is the ARIMA model needs those different stuff, and the second is that the prediction of the ARMA model and the ARIMA model is slightly different. Okay. All right, so before moving to the R code, I want to give you an example, okay? An example, and this example is actually very important example. So this model, ARIMA 011, or sometimes just called IMA11. So it does not have a AR part. It only has an MA part on the first difference in data. Okay, right. So this is actually a very popular model. Yeah, so the model is written as xt equal to xt minus 1 plus t lambda wt minus 1. Yeah, so if you reorder, it's just xt delta xt minus 1. So that's the ARIMA 11. I mean, ARIMA 011 or IMA 11. Okay. Yeah, so why this model is very, very popular? It's actually a very popular model in finance. I think especially in the stock market, it's a very popular model. So why is it important? Why is it popular? Because this model is very easy for forecasting. Okay. Yeah, so it can be shown the one step ahead predictor or forecaster is, so this is your one step ahead, is equal to what? Is equal to 1 minus lambda. The lambda is the coefficient of the MA, okay, xn. Okay. So this is your, let's just to make notation consistent. So xt plus 1t xt, okay, so current x value plus lambda xn, sorry, xt t minus 1. Okay, so this is let's say this is your current one step ahead. This is your previous period one step ahead. Okay, so you can see this predictor just says the current one step ahead predictor is just equal to, I mean, it's a weighted average of the current x value and the previous one step ahead predictor. Okay. Right, so yeah, this is sometimes called the exponentially weighted MA. Yeah, so if you are ever seeing like any finance, I mean, especially like investment stuff, like this EWMA stuff, it's just very popular and people use this a lot to do predictions. Not to say this is a very good prediction model. The reason is that this model has a very, very nice interpretation, okay, because it's just a weighted average of two stuff, the current stuff and the previous forecast. Okay, yeah, and this lambda here also has another name, so we know it is a coefficient for the MA part, but actually this lambda is also called the smoothing parameter. So the lambda sometimes called smoothing parameter. So let's say if lambda is large, okay, then what? Then xt is small, right? And the lambda xt t minus 1 is large. Okay, so that means the current one step ahead forecast depends a lot on the previous one step ahead predictor, right? And this will give us a smoothing prediction, right? Because your current value depends a lot on your previous value. Okay, so if you like draw those graphs, it would be a very smooth graph. There won't be a lot of like jumps in those stuffs, right? On the other hand, if you have a smaller lambda, then that means your xt plus 1t depends more on xt. Okay, so that means your prediction is less smooth. So yeah, you can imagine, for example, like today's market, let's say it's, I don't know, it's hit by a large like financial shock. Okay, so that caused the stock market to say, let's just say like drop, like decline 5%. And if you have a smaller lambda, okay, then you will predict that the tomorrow's stock market price will be also will also be below, right? Yeah, because this depends a lot on the current x value. However, if you have a larger lambda, then you will think that, okay, even though I have a large like shock today, but tomorrow's prediction won't be that bad because it depends a lot on my previous one step ahead forecast. Okay. Yeah, and also the question now comes to how can we determine this lambda? Yeah, that's, I think, to me, it's more like a statistical question. To me, it's just like a pure statistic question, even though some economists or might or I mean, especially financial economists, they might think that's like a economic behavior question. Yeah, but to me, it's more like a statistical question. To pick those lambda, you can just use like a lot of statistic tools to pick those lambda. I think the most popular is that you can use cross-validation to pick those lambda. You basically try to make your prediction error as small as possible. Yeah, but I mean, those financial economists, they might start from like the economic theories or the individual behaviors to decide that lambda. Yeah. Okay, but anyway, what I want to discuss here is that this ARIMA 011 model is a very, very popular model. And the reason is because it is very easy to forecast. Yeah. Yeah, and also, I think I forgot one thing here. Yeah, and moreover, or I mean, more importantly, the MSPE of this IMA11 model is very easy. It's just equal to it's just equal to this very clean formula. And this part, very easy to solve, only depend on n and lambda, right? Not depend on those side j's. Okay. Yeah, so if you are doing like a ARIMA model, then the MSPE depends on those like infinite summations of the side j's. But here it only depends on m and it only depends on lambda. Okay. Yeah, and also you can see as this m goes to infinity, this part in the bracket also goes to infinity. So it won't converge, it just diverge. Okay, so this is very different from the ARIMA model. I mean, this is very different from the ARMA model. So in the ARMA model, the MSPE, the prediction error will converge. But here, for once you have like those non-stationary condition, I mean non-stationary feature in your data, then your MSP will diverge. Okay? And this can be very easily seen because this M will go to infinity. Okay. All right. Okay. Yeah. So I think that's pretty much the theories that I want to cover for the ARIMA model. Yeah, so I do the definition of the ARIMA model. I do the forecasting, which is slightly different from the ARMA model, and I also give you this very popular example. So IMA11. Okay, yeah. So later, if you took the finance course and also I think the investment course, you definitely will see this. Okay. So now I think I want to move back to the R and let's see some examples of the ARIMA model. Okay. Okay, so this first example is just an illustration of how to run the ARIMA model in R. So a couple of ways that you can run this ARIMA model. So the first is that you just ignore this D. So just set this D equal to 0, okay? But you do this difference on the data itself, okay? So let's run this model. This is what we seen in last class, okay? So we do this like diff on the log varf, okay? And then we run a MA1 model, okay? All right, so this is first differencing on the raw data, then run MA1, okay? And another way that you can imagine is that we do not take the first difference on the raw data, but what we do is that we specify 1 here, okay? Yeah, let's check the coefficients. So the coefficients for this model we got is negative 0.77. And for this part, I think, we also got negative 0.77. Okay, so this is that you can run IMA ARIMA 011 directly. Okay. Yeah, so this two give you exactly the same result. And this is not surprising. It's just like 2 different procedures. One is to take the difference first, and the second is basically is to ask the computer to take the difference for you. Okay. Okay, so that's the example number 1. And example number 2, we will see, we will start with this. Okay, so we will start with a model, which is a AR2 model. T minus 1 plus, sorry, minus x t minus 2 plus wt. Okay, so we will start with this model. So we will start with this AR2 model. Okay, as we said, whenever we start with a model, we will check whether this is a valid ARMA model. And to check this, we can check whether it can be represented as an infinite MA process and an infinite AR process. And those infinite process, the coefficients of those infinite process gonna be converge. Okay, so we can check this. And we realize that the coefficients diverge. It does not converge to 0. It actually diverges to 10. And if you like take the summations of all those coefficients, it won't be less than infinite. It's gonna be equal to infinite. Okay. So once we check that, we will see this is not a stationary model. And the first difference of this model is actually diff xt equal to 0.9 diff x t minus 1 plus wt. Yeah, and if you take the difference, you will realize that the difference of this xt is equal to 0.9 difference xt minus 1 plus a y noise. And we know since this coefficient of 0.9 is less than 0, sorry, it's less than 1, so this is a stationary model. Okay, so this is a okay, so then we want to use this model to do some forecasting. Okay. So this is, so all this code is to forecast, use to use this model. Okay, so we first like set state to this 1998. Okay, then we generate X. Okay, so this X again is generated by this ARIMA simulation. Okay, so it has order 110, right? Because it's an AR1 and we take the first difference. So it's a 110 model. And the coefficient for the AR part is 0.9. And we generate this time series data 150 times. Okay, and we will just use the first 100 data points. Okay, so we generate this. Let's put here. We generate this data 150 observations. Okay. And we use the first 100 observations to do prediction. Okay, so this Y is the first one. It's the first 100 observations, and this X is our total data generation. And what we want to do is that we want to compare our forecast and with our true data. Okay, so here's we do the forecast. Forecast based on the first 100 observations. Okay, yeah, you can say you will just use the S ARIMA 4, and the data we put in is Y, and we will do 50. We will do 50 predictions, and the order of the model is 110. Okay, so let's do this. Okay, so this graph is can be viewed as this. Okay, so the first 100 observations, so which is this black line. Okay, so this is our raw data. Okay, and which is also Y in our data set. And this red dots, there are 50 red dots here, and all these red dots are our predictions based on our first 100 observations. And these shaded regions are the confidence intervals. And you can see that these confidence intervals actually do not converge, right? Just recall the MSPE of a ARMA model, the confidence interval will converge, but here it will diverge. And I just explained that. The reason is that we have this non-stationary component in this model. So it is not surprising that the mean square error, the mean square prediction error, or this confidence interval will not converge; it will diverge. Okay, so okay, and now let's put our true data back to this graph. Sorry, let's put our true data back to this graph. Okay, so this black line from 100 to 150, this black line is our true data, okay? So what you can see from here is that our prediction actually does a pretty good job, right? So this right line pretty much overlaps with this black lines, okay? So that means this prediction is pretty much consistent with our true data, so which is pretty good, right? And actually says that this is a very good model to do prediction, okay? So the conclusion is that our prediction does a pretty good job, okay? Right. Yeah, but I mean, unfortunately, this is not always the case. Okay, so what I do is that I only change like the set state, so which is the data generating starting point. I change it from 1998 to 2000. Okay, and we regenerate some X values based on this model. And we will take the first 100 observations for prediction. So we do the prediction. Okay, so that's our prediction. The prediction pattern, you can see, is pretty similar to the first graph, right? So it's an increasing pattern. However, let's check our true data. Oops. You can see this black line is our true data. Right, so you can see it is very different from our prediction, right? Our true data has this decreasing pattern, but our predicted data, which is this red dotted lines, has a clear increasing pattern, okay? Yeah, so this is that this prediction does a pretty bad job. Yeah, but you still cannot say that they are doing the wrong thing, because our true data is still within this confidence interval. Okay, so even though it is at the borderline of this lower bound, but it is still within our confidence interval, it's still within our 95% confidence interval. Yeah, so even though like you can see that, I mean, this prediction is basically useless. I mean, if you want to use this prediction to trade in the stock market, you will do totally the opposite thing. But I mean, just from the mathematical perspective, it is not wrong because it is still within the confidence interval. Okay. Yeah. So this just says that just if we change like the data generating process a little bit, then the model might not do a very good prediction job. Yeah, but there's nothing wrong with this like ARIMA 110 model. It's just like this model is not good enough to capture all the patterns in the raw data. We need to introduce like more features. We need to introduce more ingredients in this model in order to capture like this decreasing pattern. Okay, so I think later in the class we will see like a threshold regression, and we will also perhaps we do not have time, but there's also some literatures about like this like this. I mean, this like jump patterns of the raw data. Yeah, but we don't have time to see this. Yeah, I just want to point out that the ARIMA model we have seen right now sometimes does a pretty good job, but in many cases it won't do a pretty good job. And as we build on our knowledge, we will like introduce more components and more features in our data in order to capture this decrease. Okay, so here the conclusion is that okay, so any questions? Okay, so yeah, if there's no more questions, I think that's it for today's class. I will just stop here, and the exam is next class. And if you have any questions about the exam, so please let me know. Okay, so thank you very much.